So certainly the hardware layers are extremely important, for enabling the system, right? We need reliable transmission and retrieval of qubits. We need to correct and mitigate for these atmospheric effects. We want to make sure that the quantum communication is actually working at the lowest layers. So, what components do we use for generating these quantum signals, for reliably detecting them? What components and subsystems do we need, on the payload, but also on the ground station? And then moving up to the link layer, or the connection layer, this is about thinking about the channel, right? What are the properties of the channel? How can we best link our nodes together? How do we combine these components at the physical layer in a way that we can most efficiently produce our quantum signals, transmit them, and detect them, and correct for any atmospheric turbulence and these wavefront distortions, etc. So Suparna, we've spoken a lot about hardware and sort of system design, but can you touch on these upper layers of the system that we're going to need to move this away from scientific demonstrations and into an infrastructure and an operational system that we can use?
Yes, surely. The higher level layers, which are the protocol layer and network layer, they are the crux of whether we are performing a certain kind of a QKD or protocol. These are essentially covering all those aspects of whether we want to be modulating the quantum signal in a certain way. We should expect to see some imperfections in the photonic connection layer, and how are we going to manage those imperfections? How are we going to make corrections for it? As the qubit traverses through the link, there is going to be bit flip errors, phase flip errors. Like how do we mitigate these errors? Error correction. All of these comes under the protocol layer, and then the more higher level is going to the network layer, where we design the routing, the best way to route between two nodes that need to be communicating at that point in time, need to be distributing keys between them, or just have entanglement distributed between them. How do we optimize for the overall performance in terms of fidelity of the state, in terms of key rates? All of this comes together here in the network layer, and like we can already see, these layers are very much dependent on design of the system, and the software plays a key role in also allowing the user to interface with this hardware layer. So I would it would be great to hear, Mike, your thoughts on how software plays a role in designing and orchestrating all of these features in these higher level layers.
Absolutely. I'd be remiss as someone who works in this industry and works for a quantum networking company, mainly focused on software. We did want to emphasize the critical role that software plays. I mean, we spoke a lot about the hardware landscape, the system level design, wavelength selection, orbital selection, link direction, all of this. And it can be a lot. It can be daunting to begin to break this problem down. And as we're designing, right, we really want to be able to accurately simulate and emulate these systems, so we can make the best choices for, which hardware components do we select? How do we select the optimal wavelength? How do we maximize the performance of the system under these stringent constraints of size constraints, weight, power, and cost as well? How do we begin to design these optical ground stations and the subsystems that they're going to need, both from the quantum signal mitigation, but also pointing, acquisition, and tracking in these systems, timing and synchronization. There's a lot of plumbing and underlying systems that need to be designed and interoperate together. And as we're designing these systems, testing the hardware, assembling the payload, assembling the optical ground station, we're going to want to do many experiments and testing on Earth right before the launch. So how do we validate these experiments that we're doing on Earth and doing the testing? Does it align with theory? Does it align with what we expect? Or is it matching the spec sheets of all the components that are being purchased? So simulation plays a really critical role in understanding the effects of an operational satellite, things like the orbital path and temperature fluctuations and things like that. How does it affect my hardware? How does it affect the system as a whole? How do I mitigate these effects to a certain extent? So simulating all these scenarios is extremely important. And we do have engagements at Alira with a variety of entities, both planning these missions, but also with our vast partners, both in the hardware space and satellite companies as well, that we can lean on to begin to break this problem down and start designing these systems and plan for the future as well. So simulation, plays an extremely critical role in designing these systems and simulating these different scenarios and tests. But when it comes to actually, operating the system, right, we don't want it to just be a science demonstration, right? We want to build an infrastructure, a quantum satellite backbone that we can leverage and build upon for the future to realize this goal of a quantum internet. So what do we need for that from a software standpoint? There are many things that we spoke about at the lower layers, but thinking of a higher layer, sort of orchestrating the system, how do we configure these devices? We don't have the advantage of having postdocs or experimentalists on the satellite, on the payload, tinkering with components, making sure things are up and running, right? So how can we do this from a software-defined networking standpoint to manage and to monitor what's going on, to retrieve metrics from the different subsystems that are involved, to manage the integration with the fiber networks that we're eventually going to need to do to realize this quantum internet. So orchestration plays a critical role as well in operation. But we're going to need a lot of software and firmware as well for those lower layers of control and communications. So a lot of these protocols are extremely time sensitive. So there's a lot of timing and synchronization infrastructure we need to rely on, calibration to understand in real time, what are the effects of the atmosphere? How is it behaving? This could be impacted by the time of day, could be impacted by the weather, the atmospheric turbulence. So having these kind of dynamic calibration systems and mitigation systems, error correction that we spoke about, and doing this in a very low latency, kind of time sensitive way will be extremely important. So, low latency software and firmware and control also plays a critical role in enabling this the system that we want to realize, right?